All right, good afternoon, everyone, technically. Fair warning, if you remember a couple weeks ago, I had to kind of take a 2-minute pause. I'm gonna have to do the same thing today, 2 or 3 or 4 minutes, around 1 o'clock, right at 1 o'clock. Sorry about that. It's kind of an every other week thing. Thankfully, it's only literally 2 or 3 minutes, but we will take care of that when the time comes. What you see up here is what I would put on the whiteboard if we were doing this class in person. This would be today's whiteboard, same as before, SOHCAHTOA. Some old horse caught another horse taking oats away. First sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent is opposite over adjacent. The three reciprocal functions. I should also have up here that sine is cosine over tangent, but that's fine. It's not the end of the world. The Pythagorean identities, your two very, 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 very important right triangles that you must memorize down perfectly. A couple quick radian conversions, which is not all the radian conversions you should have known off the top of your head. I've mentioned that pi over 2 is 90, pi is 180, 2 pi is 360. Those are also very important to know off the cuff. A smart trig class for getting the trig functions in quadrants 2, 3, or 4 based off of reference angles, things like that. The fact that sine basically takes off the properties of the y value of a coordinate, cosine basically takes the properties of the x value of a coordinate, tangent takes the properties of y over x. And when I say takes the properties, it is exactly true on a unit circle, which is how we can do the quadrantal angles, meaning the cosine of 90, the sine of 180, the tangent of 270, the secant of 360, all the 90-degree angles. So when you're using angles like 30, 60, and 45, it's these two triangles. When you're doing any multiple of 90 degrees, you go back to the unit circle, specifically the coordinates on those angles, the 0 degrees, the 90 degrees, the 180 degrees, and the 270 degrees, as well as the 360, of course, which is still the same as 0. Which I thought I had written up there. This would be 0 degrees. This is 90 degrees. 180 degrees, and 270 degrees. So if you wanted the cosine of 180 degrees, cosine goes like the x value, the cosine of 180 is the -1. That was not what I was trying to circle. The cosine would be -1. If I wanted to know what is the tangent of 270, tangent's the ratio of y over x. So you take the -1 over the 0, and it's undefined. It's very easy to quickly use this to get the answers versus blatant memorization of a unit circle that you will definitely forget 2 months from now when, or let's say 6 months from now when you're in calculus and still need that information readily available. And now you got to memorize calculus formulas on top of still having a unit circle memorized. That was just too much memorization for my type of brain, and I think a lot of our brains are that way and we don't know it. Memorization is not always the best. Logic and reasoning help us go through things, connecting dots, understanding we're all just one trig problem. Okay, so we'll refer to that some a little bit later. Let's get back to our notes. Right where we left off in 5.4, I did just type this up right before class, just kind of starting things off. Everything else was there before though. So 5.4, what did we do last time? We developed the unit circle, which is a radius of 1. We talked about how these things, the r's are no longer needed because if the r is 1, you're dividing by 1, which does nothing. We talked about how if you have to do trig functions of a coordinate pair, if those points have to be on a unit circle, which you would really have to prove unless they tell you that, then you can just say sines the y value, cosines the x. We said this is a pretty atypical problem though. We just fell back and said, hey, the unit circle is really just best for, again, doing 0 degrees, 90 degrees, 180 degrees, 270 degrees, or the radian version, 0 pi over 2 pi, 3 pi over 2, and 2 pi. We established the sines, cosines, and tangents for those 4 angles. You can memorize them if that's your preference. Me personally, I build them on the fly every single time. There's a couple I have memorized because they get used so much. Just mainly it's the sines and cosines of 0 and 90. I don't have any of these, which ones are undefined and 0, just flat out memorized in my head. I don't have these 180s and 270s just flat out memorized in my head. I go All right, cosine's the x-coordinate. The x-coordinate 180 degrees is -1. I'm anything but honest. Wait, that doesn't sound right. Is that the right phrase? I'm honest. Let me just keep it simple. So we did examples. We showed you how you can logic and reason through it. We talked about the even and odd properties. We did say that this is something that is not necessary throughout most of the class, but can be a time-saving element occasionally. There are still times when it's necessary. When we get into the next chapter, when we start doing what's called a proof, basically just proving that the left side of an equation is the right side, this issue will come up there, so don't think that you can just completely ignore it. You need to remember that cosine's even and the others are odd. So there's only, out of the three main trig functions, cosine's the only even and the others are odd. Even means a negative inside with an angle can be disregarded. Odd means the negative has to get popped out. So this is one way that we can avoid making reference angles and using a smart trig class and all that stuff by just applying even and odd properties. But if you don't like even and odd properties, you're doing it the other way. Options. Lots of different ways to do things. Okay, so last little bit of this fourth section. This won't take us too long. I've already established this idea. Periodic functions. These are functions in which, let's say t is the traditional variable of the function instead of an x. We don't like using x as an input variable too often in a trig class, but ironically we will in the next little bit I show you. So t is the variable. P is just some arbitrary number. It might be 3 or 5 or pi or 2 pi or something like that. Usually for us, those last two numbers because trig. A periodic function is one that just keeps repeating. It keeps repeating, it keeps repeating. It does the same thing over and over and over. So if you were to graph a periodic function, it might look something with better artistic skills. Imagine those all have the same heights. So let's say this is an x value of 1, this is an x value of 2, an x value of 3. The outputs, the heights, are all the same. That's what we're saying here, that some f of t, so maybe this is f of 1, is the same thing as f of 1 plus 1 is the same as f of 2 plus 1. I can just take a number and add 1 and keep getting the same thing over and over and over. Is it always 1? No, it's usually not 1. That's just the context of this example. There's a pattern that loops for eternity, and trig functions are based in being periodic. There we go. All 6 trig functions are periodic. We've established this with the idea of angles being coterminal. So 0 degrees and 360 degrees are essentially the same because they're coterminal. It doesn't matter whether you try and find the cosine of 0 degrees or if you try and find the cosine of 360 degrees. You will get the same answer because you are in the same position in terms of relative rotation. So more specifically, sine and cosine have a period of 2 pi. Imagine that I just drew the pi symbol there, which means the answers, if the cosine of 0 is the same as the cosine of 2 pi, is the same as the cosine of 4 pi, is the same as the cosine of 6 pi. Now, if you wanted that in degrees, that means they have a period of 360 degrees. But we're not going to be talking about degrees too much in some sections, so I want to get us used to talking radians a little more. So the cosine of 0 is the same as the cosine of 360 degrees, is the same as the cosine of 720 degrees, is the same as the cosine of 1080 degrees, etc., etc. So in other words, yeah, I can do it this way. Sine of t plus 2 pi, again, just imagine I wrote the pi symbol there, is the same as just doing the sine of t. And then the same for cosine. So if I ask you for the cosine of 360 degrees, that means you say, nah, I want to do the cosine of 0. Again, same idea as finding coterminal. Periodicity and coterminal angles, same concept. The rest of them have a period I'm sorry, not the rest of them. I'm just trying to say tangent and cotangent next. In fact, I'm just going to say tangent, since I'm not talking about secant and cosecant. Tangent has a period of pi. Which means the tangent of t plus pi is the same thing as the tangent of t. So in other words, if I wanted to do the tangent of 180 degrees, I could just do the tangent of 0 degrees. If I wanted the tangent of 210 degrees, I could just subtract 180 and say, all right, I'm just going to do the tangent of 30 degrees. So this is where things get interesting and lead to some small issues moving forward. Now, reciprocal trig functions have the same behavior. So if sine and cosine have a period of 2 pi, that means cosecant and secant have a period of 2 pi. If tangent has a period of pi, 1 pi, or 180 degrees, that means cotangent has a period of pi or 180 degrees. I want to scroll back up to this right here, and everything can actually be established in this blue ink right here. Look at the pattern of the answers for the sines and cosines. It goes 0, 1, 0, -1. The next thing would be 360 degrees, which is the same as 0 degrees, so it's 0. So it goes 0, 1, 0, -1. The next one would be 0. Then it would go 1, 0, -1, then 0, 1, 0, -1, 0. These four just keep repeating over and over and over. But you have to go completely full circle. You have to go 360 degrees before you actually get a loop, because it goes 0, 1, 0, -1. Kind of looks like an extra negative over here. Let me just clean that up a little. I don't want any confusion because of my poor handwriting. Same with the cosine, 1, 0, -1, 0. There's no full pattern established until you get 4 of them, a full 360 degrees. So then the next one will be 1, then 0, -1, 0. Again, just keep going in 90-degree intervals. Look at the tangent though. 0, undefined, 0, undefined. Now, it's not the complete picture, but I think it's enough to establish that because there's no ones and -1s, which is what causes us to have to go the full 360 degrees, because 1 and -1 are different, 1 and -1 are different. It just goes 0, undefined, 0, undefined. You actually have that full pattern established halfway in. So you only have to go 180 degrees before you actually see tangents looping and repeating answers. Now, there are times when people accidentally say tangent has a period of 2 pi, and the cool thing is, even saying that incorrectly, you can still establish correct answers, because it's still not wrong that the tangent of 0 is the tangent of 360. It's just that you've gone 2 periods instead of 1. Now, depending on the question being asked, you could get a right answer or a wrong answer. If it's asking you how many periods have gone by, that would give you a wrong answer. But if you're just trying to find the output, if you find the output by using that 360-degree idea, the wrong period, too much, you'll still get the right answer. It's the same thing as like if you try and add a half and a fourth, the LCD is 4, but some students might use a denominator of 8. They can get the right answer. They're just doing extra work to get it. They're doing more work. They're dealing with bigger numbers, things like that. All right, so last couple examples. What are we up to? Example 3? Yes. Example 3, evaluate by first using the trig functions period to get a smaller angle. So our goal is to, do the sine of 30 degrees or something, but it might start out as the sine of 390 degrees. That's what I'm talking about. So for A, the sine 405 degrees. And for sines and cosines, it's just as simple as finding a smaller coterminal angle. For tangent, instead of subtracting 360, you're subtracting 180. All right, well, sine has a period of 2 pi, which is 360 degrees. So you can take this extra step that some people will do, and they'll say, all right, well, 405 minus 360 is 45. So I can separate this as 45 degrees plus 360 degrees. Some people would just go to the next step and say, all right, now that you have the period added, you can just drop it and say this is the same as the sine of 45 degrees. Again, a lot of people will skip that step and just go straight to here. I don't care what you do as long as you can get it right. Show some amount of work. All right, sine of 45. This is in quadrant 1, so we don't need to do any smart trig class or even or oddness or anything like that. We can just say, oh, okay, well, that's the 1, 1 square root of 2 triangle. I usually don't draw these up to the side, but I will this time. All right, if this is the 1, 1 square root of 2, that was 45 degrees. We knew it was 45 degrees, which means this is the 1, 1 square root of 2. And the sine of that is 1 over square root of 2. But we know that we have to multiply top and bottom by square root of 2 to get appropriate answers that my math lab and your teacher will happily accept, which is square root of 2 over 2. The sine of 45 degrees is exactly the same as the sine of 405 degrees. They are in fact coterminal. It's not always the case with tangents, but it is with sines and cosines. All right, B. The, not sine, tangent of 240 degrees. So tangent has a period of pi, not 2 pi. If this was a sine, you would say that 240 degrees is already fine because that's within 0 to 360. But with tangent, its period is 180 degrees. So you can subtract 240 and 180, which would be 60. So you can say that this is the tangent of 60 plus 180 degrees. So this is the period, any multiple of the period, which means we don't even need it. So this is just the same as the tangent of 60 degrees. Now, I will say that if I didn't tell you to do, if I didn't give you these instructions, if I just said evaluate, I honestly probably wouldn't have done it this way. I would have done, all right, well, 240 is in quadrant 3, tangent's positive in quadrant 3, the reference angle is 60 degrees, and I'd end up doing the exact same calculation. It's just another way to do it. Another student might say, well, this is the same as negative 120 degrees, and tangent is odd, so I can pop the negative out and then do the tangent of 120, which is quadrant 2. Like I said, there's so many different ways to do a single trig problem. All right. Tangent of 60, that equals, let's draw out that triangle again. 60 degrees, which means this is 30 degrees. I know that 3 is a little ugly, but it's there. The number opposite the 30 is the 1, the hypotenuse is the 2, and the square root of 3 is opposite the 60 degrees. You get those wrong, the whole problem's wrong. Get it right. So tangent is opposite over adjacent. The opposite is square root of 3, the adjacent's 1. So this is square root of 3 over 1, which is just square root of 3, no rationalization needed. Finally, C, we are going to do the secant of 1500 degrees. Sorry, distraction. Now, secant is the reciprocal of cosine. Cosine has a period of 2 pi or 360 degrees. There's a bunch of 360 degrees in here though. So you would need to figure out how many 360s there are, and you can just quickly pull up a calculator. I mean, you should be able to do that in pencil paper too, but all right, 1500, I can't see that. There we go, minus 360, that's one of them. Not enough, minus 360. Not enough, minus 360. Not enough, minus 360. Boom, there we go. That was 4 of them, 4 times 360. Just so I can write a regular old number, is 1400. So I could draw this up 2 different ways. I can say this is the secant of, it was 60 degrees, right? 60 degrees plus 1440 degrees. Or I could say it's the secant of 60 degrees plus 4 times 360 degrees. That really establishes that it was 4 periods past it, but it's the same answer. Whichever way you do it, you can just say, okay, ignore all the period numbers. This should be the same as the secant of 60 degrees. Again, you can refer to the one triangle you drew up, or you can draw them on the fly. I really suggest, especially while you're learning this stuff, drawing them on the fly to get used to it. Here's 60 degrees, which says same triangle as last time. Square root of 3 goes here, 2 goes here, 1 goes here. Maybe you want to do this. Secant is the reciprocal of cosine, 1 over cosine of 60 degrees. That's an optional way. Or you can just remember, okay, well, cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. So adjacent over I've circled the wrong thing when I said adjacent. Hypotenuse over adjacent is secant. Hypotenuse over adjacent. So 2 over 1, which is 2. Again, the cosine would be a half, adjacent over hypotenuse. Secant is the opposite order, hypotenuse over adjacent. 2 over 1, which is 2. So I'm a big fan of doing this right here, using the period when you're dealing with larger angles like 1500 degrees and 405 degrees. Do you have to do it with 240? I find a lot of people don't bother, especially with tangents, especially because a lot of people forget that the period's 180 degrees. But you can't forget that, because that's going to be an important fact moving forward in this course. I can guarantee it. You'll be able to still get some problems right accidentally thinking the period's 2 pi, but you will mess up a lot of other things. It's a matter of what exactly we're doing. All right, that is 5.4. So we finished that today, which means it will be due on the 23rd. 5.4, homework due 9/23. Make sure you note that. If I don't have that set up in my math lab already, I will set that up after class. And that'll take us into 5.5. Graphs of sine and cosine functions. Actually, I'm sorry if you just wrote that immediately on your paper if you are taking appropriate notes. I want to do a problem that I meant to do a couple sections ago, a word problem. So quick, just quick word problem from 5.2 or 5.3. I can't remember which it was off the top of my head. Sorry for that, but either way, it's important. A guy wire runs from the ground to a cell tower. Wire is attached to the cell tower 150 feet above the ground. The angle formed between the wire and the ground and the wire is 50 degrees. The questions are, how long is the guy wire? And how far from the base of the tower is the wire anchored to the ground? Let's do it this way then. I don't want it to look like that. How far from the base of the tower is the wire anchored? I'm going to draw up a picture for this. You know what they say, a picture's worth 1,000 words. Now, I don't have to give you a picture for this. You can establish it from all of this. So let's say that's what we're doing, because that's really what I'm doing. A guy wire runs from the ground to a cell tower. So we're going to have a cell tower somewhere, and a wire is going to be running to the top of the wire. And it doesn't say that I'm taking this word for word, but I kind of feel like it should. But you usually don't run wires along the ground, right? It's usually from something to the top of something. So let's say right here is our tower. This is our tower. And we've got a wire attached to the top of it. And it's running to the ground. Now, this wire that's attached, 150 feet above the ground, so it's a 150 feet tall tower. It's attached somewhere over here or over here. Let's attach it on the left. So here is the anchor point. So this is your ground. Here's your wire, as straight as I possibly can without taking 10 minutes blindly doing it with a ruler. Imagine doing something blindly with a ruler. That sounds fun, because that's the situation I'm in. So this is the wire, not the wonderful TV show from the early 2000s, the actual literal wire. And then again, our ground is down here, obviously. They want to know how long is the guy wire, so they want to know the length of this distance. And they want to know how far from the base of the tower is the anchor point. So this is our ground, and we need to know that distance. So if you wanted to give these letters, the hypotenuse is the wire, so I would call that our C. And the 150 you could call the A or the B. I'll call it the A, which means this distance would be the B. And they told us that the angle formed between the ground and the wire is 50 degrees. So this right here, this angle between the wire and the ground is 50 degrees. This is, of course, a right angle because this is not the Leaning Tower of Pisa. It's built straight up, appropriately, good construction. This is what trigonometry is all about. It's what it's for. It's for word problems. Why is that happening? Let's go right there. We go. Word problems. Life is a word problem. Engineers do this kind of stuff all the time. They know they got a 150-foot tall tower. They have a little electronic device that they can measure. They can walk some distance. It doesn't matter how far they walk. They can walk. They could have walked to here. They could have walked to here. They could walk way out over here. But then they face the tower and they go beep, boop, beep, and it says there's a 50-degree angle. Pretty easy. Or you could get old school and get yourself a protractor and put it at eye height. You would have to then subtract the height from your eye to the ground in that case. You know, it's small and almost negligible. You'd get a close answer if you didn't, but it wouldn't be accurate. In engineering, it needs to be accurate. What is the point of this problem? How do we use trig to do this? Our goal is to find lengths B and C. How long is the guy wire? So that is answer C. I know it's question A, but that means we want to find out the distance C. How far from the base of the tower is the wire anchored? That's that distance right there, B. So those are the goals. What we want to do is we want to use a trig function that picks out the known value and also the one we need. We want to use a trig function that picks out the known value and also the one we need. And what am I referring to? Opposites, adjacents, and hypotenuses, hypotenuse. So in terms of 50 degrees, this 150 would be the opposite. The length of B would be the adjacent, and the C would, of course, be the hypotenuse. The 150 is the known value, so we have got to use trig functions that use the opposite. We need to use trig functions, and because there's more than one choice, I'm only going to show the work for one, but there's more than one choice. So we've got to use a trig function that uses an opposite. Now, how do we know? Because sine uses opposite, tangent uses opposite, cosecant uses opposite, cotangent uses opposite. Which of those four should we use to do A? How long is the guy wire? So we know we've got to use a trig function with opposite. C is the length of the wire, which is the hypotenuse. So we need the trig function that uses opposite and hypotenuse, which means we have two choices. We could do sine or we could do cosecant. I can imagine that you guess which one I'm going to go with, sine. Cosecant does the job, but it's a bigger pain in the butt because we're used to sines, cosines, and tangents. You might not be yet, but you will be moving forward, I hope. So for A, we're going to write the sine of 50 degrees is equal to. Now, sine is the opposite over hypotenuse. The opposite is that known value of 150 feet over. The hypotenuse is that blue distance, C. I didn't have to be blue. I'm just trying to emphasize, since I called it parts A and B with uppercase letters. Guess what you do from here? You just solve for the unknown variable. Now you might say, I've never solved a trig function. This is completely different, and you're wrong. It's the exact same thing you've done in algebra. Add, subtract, multiply, divide things on both sides to get the variable isolated and all the numbers on the other side. That was a redundant statement, but it's still important to say. Now, the variables in a denominator, how do we get rid of variables in denominators? We're going to multiply both sides by that variable. So I'm just going to rewrite it. The sine of 50 degrees is equal to 150 over c. We need to multiply both sides by c. Why do we do that? Because tops and bottoms of fractions will cancel each other out. I'm going to undo me writing the canceling, but you'll leave it in your notes probably, which is fine. Again, those c's on the right-hand side cancel. So we get c times the sine of 50 degrees. Now, you might want to put the c after it, but you might get confused and think the c is part of the angle. So I actually really prefer it this way. Wrong color. C times the sine of 50 degrees is equal to 150. And we're trying to solve for c, so we divide both sides by the number it's multiplying. Sine of 50 degrees is just a number. We don't know what it is. I'm not asking for it. We're just going to divide both sides by whatever that number is. You're going to do this 1,000 times by the end of the semester. Why do we do that? Because then these cancel, giving us just a c on the left side. So c equals 150 divided by the sine of 50 degrees. Now, depending on the formats of tests, if this was a classic, in class, in person, I would say this is the answer. But usually with applications, they want decimal values. So what we would do is round to the nearest tenth. And I forgot to write that in the instructions, didn't I? I did. Round to the nearest tenth. It's an application. While yes, analytically, 150 divided by sine of 50 degrees is an accurate answer. If it's an application, we want numbers. We want numbers our boss can understand. So we go to our calculator, we turn it on, we clear our screen. What's the first thing we always do with Trig with a calculator? We check our mode. I'm in radians, which is bad. I need to switch it to degrees. Hit enter. Hit second mode, which is quit, to get out of that. And then I can type 150 divided by the sine of 50 degrees. See, if I had used cosecant, my calculator wasn't going to be able to do that. I'd have to do a reciprocal on the own problem. Don't use cosecant. And you get 195.8 when you round appropriately. 0.8 feet. So that's the length of the wire. For part B, we wanted to know how far away was the anchor point. Now, the point of this problem is really in the real world, you wouldn't have attached the wire yet necessarily. I said necessarily, might not have. You may want to know how much wire you need first, cut it, then do the attaching. So doing the trig first would be important in that regard. Alternatively, you just throw the wire up there and cut eventually. And if you don't have a way of measuring it, you'll be able to measure it in post using trig. Okay. Next question was, again, how far away from the base of the tower is the wire anchored? So the base, that's the horizontal distance between anchor point and the bottom of the tower. We call it little b, which is the adjacent in terms of 50 degrees. So again, we want to use a trig function that picks out the known value and the one we need. Now we actually know two values, technically speaking. We now know the hypotenuse and we know the opposite. So you could say, I'm going to use the hypotenuse and the adjacent, and I'll go with a cosine. I'm going to suggest that you don't though, and here's why. This hypotenuse, we round it. When you take rounded answers and put them in trig functions and then round again, you get something known as error truncation, and the numbers over time get worse and worse and worse if you keep taking a rounded number and putting it in and getting something, rounding that, putting it in, getting something, rounding that, putting it in, getting something. After you do that, maybe 4 times, maybe 10 times, maybe 100 times, your answers start to turn into trash. How quickly they turn into trash depends on what mathematical function you're doing. There's a massive field of mathematics that just studies error truncation. It's pretty confusing at first, but it's pretty cool afterwards because it does a lot of useful things. What's the point of this conversation? Don't use rounded numbers to find something else. So try and avoid that if you can. If you can't, then use it. But if the answer is supposed to be, maybe 120.1, you might get 120.2 using a rounded value first, and it'll be wrong in my math lab. And a homework problem that's going to frustrate you being so close. You might not even go back and do it again. On a test, you'll be really frustrated, and then you'll have to email me and say, hey, check my work. If you didn't do any work, I wouldn't be able to give you credit even with a rounded answer like that. No work, no partial credit. So I'm going to suggest don't do the hypotenuse. Use the opposite because it was a perfect number, 150. We need the adjacent. What trig function uses opposite and adjacent? Tangent and cotangent. What's the simpler one? Tangent. So we'll say the tangent of 50 degrees is equal to its opposite of 150 over its adjacent of what we called b. I'm using the coloring just to help a little there. So we're trying to solve for the b. 150 degrees, no, not degrees, why did I write degrees there? 150 over b. So we multiply both sides by b to get it out of the denominator. Your variable is not always the denominator in these types of problems. It could have been the top number, in which case multiplying both sides by that bottom number, you'd actually be done. I'm giving you the most complicated ones so that you can do the simpler ones without me giving you an example. So b tangent, b times tangent of 50 degrees is equal to 150. But we're trying to solve for b, so we divide both sides by the tangent of 50 degrees. That's just a number. I'm not showing you what it is, but it's just a number. So b equals, after the canceling, 150 divided by the tangent of 50 degrees. Look at how close these answers are in their actual form, in the exact answers. When it's written in this version, it's exact. When we round, it's approximate. So it's calculator. The mode hasn't changed. 150 divided by tangent of 50 degrees. You can check the mode if you really want to. Mode, yep, we're good. So 125.86, which would round to 125.9. Be careful with your rounding. And that's in feet. So that's the horizontal distance. There we go. Oh, I missed my thing. Give me 3 minutes to make this call. Again, I am sorry, I have to do it right now. I cannot do it another time. I wish I could. All right. Sorry about that. Like I said, at least it's just a couple minutes. Even if this was in person, I'd have to do the same thing. Yes, so that is another alternative. Someone asked if you could have used the Pythagorean theorem. The reason I did not do it, it would have been fine, but you have the same issue that this was a rounded number. So injecting a round number into the Pythagorean theorem, a squared plus b squared equals c squared, would give you an even further rounded answer, and you may get 125.8, or you may get 126. It would be really close, but that 0.1 is just enough for my math lab to say, no sir or no ma'am, I don't like it. So again, that's what's cool about trigonometry. Each question has usually got 5, 10, maybe different ways that you can do things. I said I use sine here, I could have used cosecant. I used tangent here, I could have used cosecant. After having this one, I could have been stubborn and used rounded numbers and used any of the other trig functions practically involving an adjacent. But yeah, so there we go. All right, again, thank you for the patience there. Now let's go back to 5.5 and give you a second to rewrite that title in case you have to. Graphs of sine and cosine functions. We are ultimately going to do graphs of all 6 trig functions. These two are by far the most important. I put a lot more weight into them in tests. You'll see more homework questions on them. The ideas of them will be used in later chapters, whereas with tangent, secant, and cosecant, their implications are more in a calculus setting. So we'll establish the graphs, but then we really won't come back to them again for the rest of the semester. As I always say, I'm very honest about what will keep being an issue and what is not. I'm not saying that the other 4 graphs are unnecessary things. I'm saying that they won't have as much importance in our course as they will in calculus. The importances will be when we want to establish the inverse trig functions in our course. We'll still need the ideas of what those graphs are, but we won't be redrawing them 50 times. Sines and cosines, you might redraw them 40 or 50 times. So these trig functions, we think about ourselves going around in a circle, but what if we actually wanted to plot the values of sine of 0 degrees, sine of 30 degrees, sine of 45 degrees, sine of 60 degrees against a vertical axis? You know, as you keep increasing the angle, at what height would we be on a vertical axis based on what the cosine is? So the angle will be our argument, and then the x coordinate on a unit circle would be the output for a cosine, or the angle would be an argument for a sine, and the output would be the y coordinate on a unit circle. Or you can use your 2 triangles, which we'll do as well. So we will make the horizontal axis the angle theta, and the vertical axis the output of the trig function. But since we traditionally use x and y axes, we'll use these as the input and output variables. So instead of saying y equals sine of theta, we're going to say y equals sine of x. So this x right here is not the x coordinate on the unit circle. This is our theta. Again, we're using an x here because we're going to be graphing them on an xy coordinate plane. So this x is our theta, as I've just said, and the y would have been the output of the trig function. What just happened? Why did that pull up? And you probably didn't even see it pull up because it's a Zoom menu. So now x is the angle y is the output. I already said that, I just wanted to write it in a smaller notation. We are going to first create a super detailed graph to establish a much simpler version of the graph. So let's see, I'm trying to count. We're going to do like 17 points to make this graph. Kind of like when you first graph a parabola, you do at least 5 points. You do like from -2 to +2 or -3 to +3, maybe 7 points for that second case, to establish that, oh, okay, well, after you see the x and the y values, there's this symmetry and it ends up looking like this. So then later we just find out what the vertex is, we plot our vertex, and then we kind of draw it from there or from there. That's the idea of how we learn a simpler way to graph without just doing a giant, ridiculous table of values, which is what we're about to do. So we're going to take a 17-point approach and we're going to turn it into a 5-point approach. So only 5 of those points is going to be important for making the graph, but you'll have to have the shape memorized to connect the dots appropriately. And so that I don't have to take up the entire page, let's do a horizontal table of values instead of vertical. What I'm saying here is instead of doing something like this, and I'm going to erase it, x, y, instead of going 0, 1, 2, we're going to do it more like this. And again, I'm going to erase it, x, y, 0, 1, 2. That's a horizontal table of values because we're going to have so many inputs. So, x. And first, before I even write that, so graph y equals sine of x. So we're having x and y. Again, x is the angle, y is the output of the trig function. Probably going to need this whole thing. And I will do this in degrees. You could do it in radians as well. And we're going to start at 0 degrees. We're going to go to 30 degrees. Then we'll go to 45 degrees. I hope I give myself enough room. Then we're going to go to 60 degrees. And then we're going to go to 90 degrees. So there are the 1, 2, 3, 4, 5 angles we will use established in the first quadrant. I mean, 0 and 90 aren't technically in the quadrant, so 2 quadrantals and the in-betweens. Then we're going to go to 120 degrees, then 135 degrees, then 150 degrees, and then 180 degrees. Sorry about the unevenness of the bottom links. Don't worry about that, please. I'm going to have to squeeze these in a little more, maybe. Let's see. After that is 210. Then 225, right? Yes. Then 240 degrees. Then 270 degrees. What I'm doing here is I'm getting quadrantals 0, 90, 180, 270, then ultimately 360. And then the 3 angles in between them that we can do with reference angles and those 2 right triangles. So 30, 45, and 60, those are all reference angles to 120, 135, and 150. They're all reference angles to 210, 225, 240. We're going to see a lot of the same outputs with plus or minus sign differences because we're going to keep going back to that idea. Then we have 270 to 300 degrees. Then it would be 315 degrees, 330 degrees, and finally 360 degrees. Sorry, I got a little squishy at the end. I should have started at the far left. I knew better. And I'm not even going to try and use my mouse to move that. Every time I do, it fails miserably. So we're going to find all 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I was right. All 17 values, only using 3 bits of information. To fill the table, use the 2 triangles by two triangles, I mean the 30, 60, 90, and 45, 45, 90, along with quadrantals and a smart trig class. That's how I'm going to fill this table out. So you're going to keep seeing me refer back to this stuff. These two triangles, a smart trig class because we're going to be using reference angles, but they all boil down to the original angle with just a sign difference. By sign, I mean plus or minus. And for any of the quadrantals, we'll use the x and y coordinates as appropriate. All right. So for 0 degrees, that's a quadrantal. So we're talking about sine. Sine is always going to use the y coordinates when we're on the unit circle. It uses the y coordinates. So here's 0 degrees. This y value is 0, which means the sine of 0 degrees is 0. And I'm going to do the answers in blue. So again, this was a quadrantal. I went to the unit circle. I went here. I used the fact that sine is the y coordinate on the unit circle. The y coordinate at 0 degrees is 0, so the sine of 0 degrees is 0. You could actually go ahead and fill out all the quadrantals if you want to just go ahead and knock those out. Let's do that. I think that might be convenient. So let's do 90 degrees next. So we're just taking the y coordinate. Why the y coordinate? Because sine takes on y coordinates on a unit circle. So for 90 degrees, the sine will be 1. For 180 degrees, the sine will be 0 again. It matches 0 degrees. But then the sine of 270 will be -1. So 90 degrees, it's 1. 180 degrees, it's 0. 270 degrees, it's -1. 1, 0, -1. 1, 0, -1. Now I also have 360. 360 degrees is the same as 0 degrees. They're coterminal. It's a full period of sine. So this one is the same as this one. Now, you want to know what's cool? I said earlier that we're going to take the 17-point method and turn it into a 5-point method. These are the 5 points you'll use. Using the quadrantals is the easiest thing you can do for yourself because the heights are nice and easy, like 0, 1, and -1. The rest of these heights are going to be things like square root of 3 over 2 or square root of 2 over 2 or a half. It's going to be a lot uglier. So in red, I'll do the ones that use the reference triangles. So 30 degrees, here's 30 degrees. We're doing the sine, SOHCAHTOA, so sine is opposite over hypotenuse. The opposite is 1, hypotenuse is 2. So the sine of 30 degrees is 1 over 2, it's a half. So 1/2. Next up is 45 degrees. 45 degrees uses the other triangle. That was the word problem. That was earlier notes. I minimized too much. There we go. So we're doing the sine of 45 degrees. Here's our 45, or the other one if you want. Opposite is 1, hypotenuse is square root of 2. So that's 1 over square root of 2. But I'm not going to write it that way. I'm going to write it the way you've already seen several times. Oh, mailman, sorry for the distraction. Or FedEx man more specifically, or woman, didn't see the person. I keep going to the wrong document. It threw me off. Yeah, here. So this was 1 over square root of 2, but we've seen this enough to know that you multiply top and bottom by square root of 2 over square root of 2, and you end up with square root of 2 over 2. Again, the 1 over square root of 2, I'm only going to show this one time, and I'm going to erase it. We multiply top and bottom by square root of 2 to get the square root of 2 over 2. You have to have these answers rationalized in the bottom. There we go. Next up, 60 degrees. 60 degrees is right here. Sine is opposite over hypotenuse. The opposite is the square root of 3. The hypotenuse is the 2. So that's our sine, square root of 3 over 2. Wrong one again. Dang it. Square root of 3 over 2. These 3 red numbers are going to be the same red numbers here, maybe not in that order. Same numbers here, the same numbers here, but with sign differences and in different orders. And I'm gonna give you a really good way as to how you can kind of remember this. Some people would call it memorization. I call it rationalization. because there's a little logic to it. It's a little leap of faith, but there's logic to it at least. All right, so we go from 0, a half, square root of 2 over 2, square root of 3 over 2, up to 1. What are these square root of 2 and square root of 3 over 2? What are those as decimals? Let's just see it because it's interesting. Square root of 2, close your parentheses, divided by 2, is 0.707. Square root of 3 over 2, close your parentheses, divided by 2, is 0.866. So about 0.7 and 0.87. You know, call it 0.9 if you want, just to round to the nearest tenth. It's not a great way of doing it, but what I'm saying is this is 0, this is 0.5, this is about 0.7, this is about 0.9, and then 1. We are going from 0 to 1. What's going to happen between 90 and 180 degrees? Our y values went from 0 to 1. They're going from 1 back to 0. We're going to scale down. We're going to go back to the 0.9. This is what you're going to end up seeing. Then the 0.7, then the 0.5, and then the 0. And then we're going to go from 0 to -1. You're going to see the same pattern of numbers repeated in a decreasing order, but negative. And then they'll increase back up to 0. So this is a good way of, you know, quickly putting things into place if you don't want to take this super long time to establish things. But let's not cheat the system. Let's go full brass tacks. Now we're going to do the sine of 120 degrees. I'm going to need to start showing some work. The sine of 120 degrees, since 120 is in quadrant 2, this would be 120. That means you have a reference angle of 60 degrees. 180 minus 120 is 60. So the sine of 120 degrees is the same thing as the plus or minus sine of 60 degrees. That's the reference angle. Which one in particular? Well, it's going to be positive because we're in quadrant 2. A smart trig class says sine is positive in quadrant 2. You choose the positive one. Sine of 60 degrees is staring us in the face. I'm not going to keep going back to that other page anymore. So this would be the square root of 3 over 2. Which was the 0.9. I predicted it exactly, didn't I? So I bet you can guess that this one's going to be square root of 2 over 2 since that was the 0.7-ish. Let's confirm it though. How about the sine of 135 degrees? Well, 135 is in quadrant 2. So here's your 135. Sorry, this is all small, but I got to write a lot. Then that means that this reference angle ends up being 45, 180 minus 135. So this is equal to plus or one or the other minus the sine of 45 degrees. We're still in quadrant 2, so it's still the positive one. And we know the sine of 45 degrees, it's right here. It's the square root of 2 over 2. We don't need to re-show all that work. And you don't have to show yourself rationalizing denominators all the time if you establish and memorize. So as predicted, it was that 0.7 and some change number. Patterns, they're a thing. So I bet you can guess that the next one is 1/2. Let's establish it. The sine of 150 degrees would be the plus or minus. So still in quadrant 2, here's 150. Which says the reference angle has to be 30 degrees, 180 minus 150. So the sine of 150 is basically the same as the sine of 30, possibly negative. We're in quadrant 2, so it's still the positive one though. Sine of 30 degrees was 1/2. Boom. Next up, we got the sine of 210. How are we on time? 15, okay. Sine of 210 degrees. Well, that's going to be plus or minus the sine of its reference angle. 210's in quadrant 3 down here somewhere. So there's your 210 degrees. I'm going to draw the reference angle in a different color now because of the overlapping, which says this is the reference angle, not this one, not this one. That would be wrong. Remember, swaying your reference angle from the x-axis. That would have to be 30 degrees. 180, sorry, 210 minus 180 would give you 30. Remember, the goal is to get an answer in that 0 to 90 range. So the sine of 210 is plus or minus, plus or minus the sine of 30 degrees, but we're in quadrant 3. A smart trig class says that cosine's positive in quadrant 3, which means sine's negative. So it's the negative sine of 30 degrees. We know sine of 30 is a half, so just slap a negative on it. This is negative 1/2. I will not do this for every single one of the rest of them. I'm going to try and we've established a pattern here. So I bet you can guess that the next one, if this is a half, it's probably going to be square root of 2 over 2 and then square root of 3 over 2, correct? Question mark? No, it's not correct. It's close. It's very close. None of the numbers I've written are wrong, but I didn't write them as negative. Negative square root of 2 over 2. I didn't leave myself enough space, otherwise I wouldn't erase that. And negative square root of 3 over 2. Don't believe me? Sine of 225 degrees is plus or minus the sine of, let's see if we can get a reference angle. You can probably figure it out based on patterns and such by now, but if not, that's okay. You can always show all your work. That's 225, which puts our reference angle as just this little bit. 180 and 225 subtracted in the appropriate order gives us positive 45 degrees. So there's our reference angle. We just said that sine is negative in quadrant 3, so pick the negative. You could have saved yourself a step of writing if you remembered that. I'm being meticulous. The sine of 45 degrees was the square root of 2 over 2. So this is negative square root of 2 over 2, as predicted. So I'm going to skip the work for the 240 degrees. I would like you to prove that it is negative square root of 3 over 2 on your own time. That would be an excellent exercise for yourself. I'm not asking for you to show me that. I'm just saying it would be good practice for yourself. But it will end up establishing that. Your reference angle ends up being 60 degrees. 60 degrees in a sine is square root of 3 over 2, but it'll be negative because you're in quadrant 3. I will do the 300, but I'll skip the next two after that because we can probably get the pattern and establish the rest. So the sine of 300 degrees would be plus or minus the sine of its reference angle. To get the reference angle, 300 is in quadrant 4, so we're spinning almost all the way around. That's our 300 degrees. Reference angle swings from the x-axis, not the y-axis, so that. If this is 300, you got to do 360 minus 300, which is 60. So the sine of 300 degrees is the same as maybe plus or maybe negative the sine of 60 degrees. Well, 300 degrees is in quadrant 4. A smart trig class says cosine's negative in positive in quadrant 4. I think I said something wrong earlier. I think I said that tangent. I meant to say tangent. I said cosine for this one, but I still had the right answer. Quadrant 3, tangent's positive, all others are negative, which is why we were choosing negative for quadrant 3. Quadrant 4, a smart trig class says cosine is positive in quadrant 4, all others are negative. So sine of 300 is the negative sine of 60 degrees. Well, sine of 60 we established was the square root of 3 over 2, so this should be negative square root of 3 over 2. Negative square root of 3 over 2. The pattern says the next one's going to be negative square root of 2 over 2. I mean, all the ones that have 5s tend to be the ones that are 45, right? I feel like that's pretty logical. And the 45 is based off square root of 2 over 2. It's just a matter of whether it's positive or negative. Quadrant 4 angles, negative for sine. And then 330 would be negative 1/2 because the reference angle would be 30 degrees. Sine of 30 is a half. Quadrant 4, though, so negative. There are our 17 points that we need to make a graph with. Oh boy. All right, 10 minutes. I am going to try and copy paste this just to have it all. There we go. Okay. Ooh, that didn't work, did it? See, that when you try and move things manually like that, that's when things go wrong. I just want this a little higher, please and thank you. Oh well, I give up. Good enough. There's our table of values. So now we actually go to make our graph. So I don't have any negative angles, so you're going to see that I draw this as a very heavy right-sided graph. So here is x, which is our angle, and here is y, which was the sine of the angle. I'm not saying y times sine of x, I'm saying that's what it's referring to. So the horizontal is the angle, the vertical is the sine of the angle, the ratio of its opposite to its hypotenuse. The largest value out of all of this is a positive 1, the smallest value is a negative 1. So let me make the highest heights of this a 1. Let me try and make this the same distance. This is gonna go, I've never had to do this with my tablet yet, so I'm hoping I can do this as best as possible. Let's try and get a good division of this by saying, all right, the 360 degrees is the largest we're going to, so let's make this 360 degrees. The middle one is 180 degrees. This looks like about halfway, as best as I can approximate it. Might be a little right heavy, but that's not the end of the world. So here's 180 degrees. Halfway between 0 and 180 would be our 90. Halfway between 180 and 360 would be our 270. But then we got to put the 30, 45, 60, all those others in. And it's not just going to be boom, boom, boom. It's not going to be an even division. It's not going to look like that. These are actually clustered. 45 is halfway between 0 and 90, so this right here would be the 45 degrees. But the distance, this right here would be 22.5. We're supposed to have 30, so 30 can't go there. It needs to be squeezed in a little more. And the same idea for the 60. It needs to be a little closer to the 45. So it ends up looking something like this, where these three are kind of clustered and there's gaps. I'm going to choose a different ink color for those. So this was 30 degrees and this was 60 degrees. And the 45 degrees was the main one. Boop. All right, so next up, between the 90 and the 180, we got our 120, 135, and 150. 135 is the halfway between, so this should be about 135 degrees. And then kind of cluster them the same fashion, like so. So that'll be our 120, and this will be our 150. Halfway between 180 and 270 would be the 225. Then cluster them around that for the 210 and the 240. Halfway between 270 and 360 is the 315. Then clustered around that, cluster, would be the 300 degrees and the 330 degrees. If you can make this big enough to not have to have these all weirdly spaced, and by weirdly I mean the orange number versus the black number, if you can have them exactly aligned, that'd be great. But I can't make this big enough and be able to show everything all at once. Not with my handwriting. And let's do the graph in red. So the graph's going to be in red. So the coordinates are read vertically. So this is a coordinate, 0, 0, 0 degrees, 0 up or down. That's right here. In fact, I'm going to go ahead and do the blue ones first. So I'm going to do the 90 degrees and 1 next. So we're going to go right 90 and up 1. Then I'm going to do the 180 and the 0. So we go right 180 degrees and up or down nothing. Then I'm going to do the 270 and the -1. So 270 and -1, we go right 270 degrees down 1. And then finally the 360 degrees and 0. So we go right 360 degrees, up or down nothing. These 5 red points are what you will be doing on your own. Those are the quadrantals. But if you only do those, this is what you might think originally. You might think that the graph is just like this, like a V wave or a square wave. Well, that's not a square wave, just a V wave. But that's not what it looks like. Usually in math, things curve, they bend. And when you put in these red numbers, which are still going to be red points, that'll confirm the bending. So these heights, 1 over 2, square root of 2 over 2, square root of 3 over 2, that's a 0.5 roughly, a 0.7 roughly, and like a 0.9 roughly. So I'm going to need those labeled as well as I can. So here's our 1/2. Then in orange, I'm going to do the square root of 2 over 2, which is like 0.7, not 0.75, so not exactly halfway between these, just a little lower. So we'll have that be the square root of 2 over 2. And then 0.9 will be a little closer to 1, actually. Like that, maybe. And that'll be our square root of 3 over 2. Same thing on the below. We'll have the 1/2 is halfway between 0 and -1, but it's -1/2 now. Then we'll have the negative square root of 2 over 2, just a little less than halfway between those. And then the negative square root of 3 over 2, about there. All right, graph in blue. Oh, red for the points though, sorry. So 30 degrees, comma half, right 30, up a half, boom. 45 degrees, square root of 2 over 2, boom. 60 degrees, and then square root of 3 over 2, boom. This looks like a straight line here, but because of the bigger gap here and the smaller gap here, that's what causes it to do this. Now I'm going to erase it after I do this because I want to do it all at once, but this is the type of picture you end up getting ultimately. It kind of bends. All right, let's get the full picture. Then from there, we're going to start bending down. So 120 degrees is the height of square root of 3 over 2, so about here. Then 135 had that square root of 2 over 2 height. 150 degrees had the height of a half. There we go. And then we're here for the 180. 210 was a -1/2 of a height, so about here. Does that look good? That looks good enough for government work. Then 225 is the next lower one. 240 is the next lower one. I have my degrees just a little too far left on that one. That's okay. So my image isn't going to look perfect over those dots, but you get the idea based on the first one. This first one's really good. The second one, not so much. And that's why I don't suggest you ever do a 17-point approach for an actual problem. Unless you're going to ruler out everything, this can look funky. And then the same idea coming back up from 270, 300 degrees, your height was the negative square root of 3 over 2. At 315, our height was the negative square root of 2 over 2. And then 330 was the -1/2. That one actually looks pretty good right there. And I can kind of see these points are just a little high. I'm going to use those other, I said erase. I'm just going to try and kind of mimic the heights just to make it look a little better. That looks a little better. So when you connect all your dots, a nice smooth curve-like fashion. Sorry if there's little bumps along the way. I don't want to draw this in one move. I'll never get it right. Let's see, that one wasn't perfect. Let's try again. Awful. I'm telling you, doing this blind is a challenge. So that red dot's just a little far to the left for my taste. I'm just gonna fudge it a little. It's okay, nothing wrong with that. And then here, you get that same shape, it's just upside down. So something like this, steeper at first and then flattens out, flat, and gets steeper and steeper and steeper. Oops, that was bad. There we go. That is one wave of a sine function. You know why we call it wave? Because it looks like a wave. You know those things in the ocean? They kind of act like sine waves. You know the things you hear? You don't hear them as waves. You can't visually see that, but they're waves. You know, the light you see, the way you can see everything, light travels in waves. This is the shape that light, sound, water, moving, all travels. Giant, freaking giant field of mathematics. So again, this is not how we will do things, which we are out of time now. So I already introduced it, but your graph, and this is where we'll start in class next time, you would just plot this point, this point, this point, this point, and this point, and then make the shape from that. So you would just have, you plot your 0, your 1, your 0, your -1, your 0, and then you make a nice pretty wave because you've established the shape. Now in my math lab, your homework makes that shape automatically for you, which is a bit too easy in my opinion, but you still should be able to do this by hand. I am considering maybe 1 or 2 questions that I grade by hand for the first test. I'm not guaranteeing it, but I'm considering it. So we will get into this and actually establish things like amplitude, period, phase shift, and all that stuff next time. We have only just begun. We've only just established the picture that we'll be using. We will not have to do all of this to make a sine graph ever again. 5-point approach, and the number of patterns pretty easy to remember. 0, 1, 0, -1, 0. All right, so we'll call it a day. We'll finish this section next time on Monday after the weekend. So have a good weekend, have a good day. Email me with any questions, and take care. If it'll let me end the meeting. Weird.